Good afternoon, YouTubers. Today we're going to be analyzing this problem here. We have a boom as shown here, and that boom has two forces. One is F2 and the other one is F1, but it also has a tensor T here as shown. And that tensor, according to the problem, the boom is intended to support two vertical loads, F1 and F2. If the cable CB from C and B can sustain a maximum load of 1500 Newton before it failed, determine the critical load F1, and based on the fact that F1 here is 2F2, that then we only have one variable, and also what is the magnitude of the maximum reaction at pin A. You can analyze this problem basically using vector analysis and also scalar analysis. Vector analysis is, I would say, is a kind of an overkill because this problem is in 2 dimensions, but yet it shows you the power of vector analysis, and it gives you a good practice when you are in 3 dimensions, because basically I'm gonna set up the basic how to do vector analysis for even a simple problem like this, which eventually can scale up to a 3 dimension without any issue. So basically this is what we have. If I recopy that problem just to make the story and do kind of a free body diagram of what I really care, which is this bar here. That bar there basically has it is basically at 30 degrees from what I'm gonna call the X axis versus the Y axis, and versus, if this is 3 dimensional, will be then we will have a Z axis here. So the Y axis in vector analysis is associated with J versus the X, and versus X axis, which is basically associated with I, and whatever happened here on the C axis, it is associated with K. And this bar basically what the problem says has one force here and another force here at some distance, and that distance is about from here to here is about 1.5 meter, and from here to here is about 1 meter. And there is a tensor T here doing like this, and that tensor is going, actually let me redraw that tensor a little bit better. That tensor has a hook here, and that's basically it. And the problem asks to calculate what is F, in this case what is F1, what is F2, but also here there's two forces. This is a pin, and a pin only has these two forces, one, and that pin is called A, so this is going to be called AX, and this is going to be called AY. And as shown, the free body diagram here, we only have to care about these forces. There's no moment here. A pin cannot sustain moment, so the moment at point A, I want to assume always this direction, positive in that direction equals 0. So what else we have? That this tensor has a slope, according to the diagram, is a 3, 4, 3, 4, 5, and that's basically it. Now here's the story. We're gonna do vector analysis. Vector analysis requires that you take some cross product between what we call the arm versus the force vector, and this is the tensor. The tensor is about according to the problem 1500 Newton. So where we start this problem, let's do this like, for example, defining what we really need to do in order to calculate the moment at A, because when you take the moment at A, then these forces here, which is this one is called F1. Let me get here the glasses out so I can see this better. So this is F2, and this is called here F1, and according to the problem, F1 is equal to times F2, and that's what we're going to do now. We're going to solve that problem using cross product. Hold it for 1 second here. There we go. Now, this is what we're gonna do. The moment at A, taking, in fact, I don't have to take any direction because the direction will be taken by the system itself. MA, this is the only thing that is important. MA equals 0. With that said, then what we need is the distance from A, and this is to B, that arm, R, I'm gonna call R, A to B, multiply by, and this is a vector, by the tensor vector. So this vector here that goes toward this direction, we need to break that in its I and J coefficients, and then we need to multiply. So we take care of that one over the bar. So now there's something, another force here which is called F2. So, and it also has the same arm, so plus the vector RAB cross product with F2, which has to be in a vector notation, plus this force here, which is basically 2F2. So we have this small arm, which is going to be called, let's call this point D here. So the distance from here to here, let's call that RAD, that vector, cross product with 2F2, which happen to be a vector as well, and all that has to be equal 0. So that's what we need to do in order to do vector notation on this problem. And so ensure that you have all the forces. Like for example, when you take the moment here on AB, I don't care about AX and AY because you are taking the moment right here, there's no arms. But when you take the moment, for example, for B, I mean for the tensor, there's all this arm which is reflected in between the distance AB. And how about F2? The same. How about F1 here? Well, that's half of the distance, so that's what I change the arm, and that will do. So what is left is, let's start to calculate what is this vector RAB. That vector is basically, you are moving to B. So let's do this very simple. You have a BX on that point, but also you have a BY, and it just happened that on the Z direction is 0, there's nothing, and you're going to subtract the origin of that point, which is happened to be 0, 0, and 0. With that said, basically what is left, or we can do the math here, vector AB is basically BX, BY, and 0. This minus this, this minus this, and this minus this. So you have that. Now the question is, what is BX and what is BY? BX is the distance up to here, is the distance on the X, so this is called BX here. And what is BY? BY is then this distance here. So BX is very simple, it's the distance here, so that would be the full distance of this guy, so that's going to be 2.5 multiplied by the cosine of 30, and that will provide the BX times the cosine of 30. If I get a calculator here, that's about 2.17. How about BY? Well, BY is going to be 2.5. Now I need this distance, so that obviously is the sine of 30, and that's about 1.25. So basically, then what is RAB is nothing else than 2.17, 1.25, 0, or in vector notation that would be 2.17i plus 125j plus 0k, and that will do. So we got the first vector. Now what else we need? We need the other vector, which is called RAD. What is that? Well, basically the same as we did the other one. That would be dx dy and 0 minus the origin of that vector, which is 0, 0, 0. And I'm using this kind of notation so that you understand that this vector has a direction, and is coming from where I'm going to take the moment, so where the distance eventually that the vector is located in, or the location of that point with respect to either the x distance versus the y distance. Then AD, that vector, is nothing else than dx dy 0. End of the story. This minus this, keep doing this, and this minus this is this, and this minus this is this. So we only need dx, and for dx, be careful here. The position is pretty much the same as last time, but we are here, and is this distance on the hypotenuse 1.5, so that is about 1.5 times the cosine of 30. That's equal 1.3, and then the dy is 1.5 is the hypotenuse times the sine of 30. That's for the elevation, and that's about 0.75, meaning that our vector RT is nothing else than 1.5, 1.3, 0.750, or in vector notation, that's 1.3 I plus 0.75 J plus 0K. No, nothing on that axis. So we got the two vectors. Now I need the tensor T. Well, T in vector notation, as in general, for any vector, you can write that as the magnitude of T multiplied by the unit vector, that by definition is that vector is going from B to what's this point here? That point is C. So we are going from B to C divided by the magnitude of BC. We can do that, and we're gonna get an answer from doing this, but also it's very straightforward to understand based on this law, and I can do it right here, that T, in vector notation, you can take it from here without getting the point, just because I happen to know what's happening with it. Like, for example, it's gonna be 1500 multiply, like, for example, if you want on the x direction, that would be 4/5. Remember, but it's going back there, it's going on the negative x, so there's a negative here, and that's going to be I, because I already know the magnitude, plus on the y direction, that would be 1500 3/4 3/5, and that's going to be on the y direction. So if we break this down, that's going to be about negative 1200 I plus 900 on the j direction plus 0 on the k direction. So that's the notation, when basically you can do that because you're in 2-dimension, and it's very straightforward to see the angle and everything. But if you happen to be in a 3-dimension scenario, then it's better to go through this route. So the first thing that I need is RBC. As always, you are going from B to C, so the last point that we need is where we are going. We are going here to C, and that's important. So basically I need RBC. If you going back here, sorry, let me see if I can shrink this a little bit more so you know what I'm talking about. Like, for example, C is located at 0 here, at 0 distance on the X, but then is located at a CY elevation, and then 0 on the K, and that you need to subtract the point at B, but the point at B is at BX by and 0 as well. So RBC equal, it's going to be 0 minus bx is going to be minus bx, 0 minus bx, so we have cy minus by, cy minus by, and then 0 minus 0 is 0. Perfect. So we got the point. What we need, bx is known and by is known. What we need is cy. What is cy? Actually, cy is the total height from 0 to where this point is located. And to locate that point, basically, what we need to do is we know this distance here. That's by is known. So cy basically is by plus this triangle here. Let's redraw that triangle somewhere here. And that triangle has this is the slope of this guy. Well, let's put it right here. It's 3/4 on 5. So, and I need this distance. Let's call that distance y2. So I need a y2 here, and that will do. I know this distance here. That distance is from here to here. That distance is called bx. So we have bx. Now, in this case, what we need to do is the fact that, let me do this like this, y2 over bx has to be the same as this. So that means 3/4. 3/1/4. So that basically what it is, just have to do with the tangent. You can do it by the tangent as well if you get this degree, but this is easier. So we end up saying that y2 is 3/4 times bx. And if we do the math, y2 is equal 1.63. So eventually, in this case, by was right here somewhere. By right here, 1.25 plus 1.63, and that end up being about 2.88. So we got that. Now RBC finally is bx, and bx we got it here somewhere. It's minus 2.17, and then we have cy minus by. That's y2 again. So that's 1.63 positive, and now this is 0. That's the K position. So we got that. Now, following this type of structure to get the tensor, then what we need to do is get the magnitude of RBC, which in this case is equal to the square root of negative 2.17 square plus 1.63 square, and that's about square root of what? 7.37 is equal to 72. And now finally, so when we substitute all that here on the tensor T equal to the 1500, that's the magnitude, multiply, and be careful here, RBC over the magnitude of RBC of that vector, then what we have is negative 2.17 divided by 2.72 here, and the other point is positive 1.63 divided by 2.72, and the last one is 0 over 2.72. We don't care. And when we break that out, it ends up being that this is approximately 1500, and guess what, this is negative 0.8, and this is positive 0.6, and this is 0. 0.8 and 0.6 are well related to this. If you are interested on this point, that's the 3/4, and if you are interested on the x, that's the 4/5. Oh, sorry. If you are interested on this direction, that's 3/5. But when you are interested on the x direction, that's going to be 4/5, and that 4/5 hit the minus point A, and the 3/5 hit the 0.6. So this eventually, the vector end up being about 1200 on the I plus 900 on the J. It took a while, right? So no wonder vector notation is a little bit harder, because even to get something simple like this, that we got the same answer just by looking the slope of this force, and we got that long time ago, like here. So anyway, I'm just demonstrating. If you happen to be on a three-dimensional scenario, then things would be very different, and this is the very robust way to do it without any mistake. So you got this. Now I got the tensor. What is left? Let's see if I got anything left. I don't think so. I think that I got everything that I need. Let's check on the math here. I need this arm times the tensor. I got that. I need this arm. I already have time F2. Oh, I need F2, and I also need well, F2. I need that vector, and that vector F2 in vector notation is equal. That vector is only have direction going down and a magnitude. So basically is F2 times 0 and minus 1, because it's going down on the y, times 0 on the k. There's no k on that vector. So it's going on the negative direction, so end up being only minus F2, and that would be on the j direction. See? And it's already on the vector notation. So we got that done of it. Now what we need is to go back and redo this math here. Let me copy that. Let's see if I can copy. Alright, so that's where we are. Now I need to do these three cross product equal to 0 to solve for F2. Basically that's what this boils down to. Let's do the first cross product. So I have an I, a J, and a K, and the cross product is R A V vector right here. It's 2.17, 1.25, and 0. So we go back here and we put 2.17, 1.25, and 0. Now we need the tensor. That's negative 1200 and 900 here and 0 here. So that's the first part, plus the second part, which is again I, J, K, and we have 2.17, 1.25, and a 0. And now I need for that one F2, but F2 is 0 minus F2 and 0. There's nothing else. And now for the last one, which is this one, and that one happened to have a shorter arm. That means plus I, J, K, and now I have RAD. Where's that? Right here. It's 1.3, 1.3, and 0.75. So it's 1.3 and 0.75 and 0 on this one. But then the force there is 0 minus 2F2 and 0. So that's basically it. We solved that and we're gonna get our result. Let's do the cofactor here. This is plus minus plus, plus minus plus, plus minus plus. And now let's get the math here. The first one, when you get this, just to get the matrix, just to get the determinant of this 3 by 3, is this by 0 and this by 0. I don't care on the I. So I is multiplied by 0. How about when the j, minus j, when you get this done like this, right? This by 0 and this by 0, that's 0. So I don't care. Plus k, and what is left on the k? Well, the k is important because there's numbers. It's 2.17 times 900. 2.17 times 900 minus 1200 times 1.25 for the first part. So this is the result of that first part, and it just happened that that's about 3, 4, 5, 3, and only on the k, only stay on the k, because everything else. So in other words, whatever the moment is happening here, if this is allowed to turn, definitely it's going to be on this axis. See? And that's perfect. And let's get this back. So I got the first part. How about the second part here? The second part, let me move this a little bit better so that it looks a little bit better. Alright, so this is the result of this first determinant. How about this one? This is happen the same. You get this out and this out. This is by this and this by this. That's 0. 0 on the I. How about the j? On the j, this by this by this and this by this, 0. So only thing left is on the k. So k is gonna be 2.17 times f2, and that's negative. Alright. How about this one, the last one, plus I? It just happened that this is by 0 and this is by 0 is 0. So how about the j? The same. How about the k? That is, when I get the k here, let's get the k there, is basically this value times this value is 1.3 times 2 f2, but that's a negative, minus this, that's 0. So what is the story here? The story that all that has to be equal 0. So the story is 3, 4, 5, 3 plus, in this case, minus 2.17 f2. Notice that we are adding everything that is on the k-axis. Minus 1.3, oops, this is 1.3 times 2, 1.3 times 2, 1.3 times 2, and that's f2 equals 0. So breaking this apart, we have this can go the other side, so we can use the distribution here, distributive properties. That's going to be 2.17 plus 1.3 times 2 equal 3453. If I add these two guys, f2, that's about 4.77, 3453. So f2 equal 3453 divided by 4.77, and that's gonna be, I haven't done, let's see, 723.9 or 724 Newton. That means that F1 by the definition here, F1 was 2 times F2, so F1 2 times F2 equal 48 Newton, or about 1.5 kilo Newton, and that would do. at least for the force. And so we got the force. Now to get on our free diagram, let's see where it's right here. To get something got deleted here. I don't know what happened, but we can put it back. Um, you know what was deleted is a force here called AX and another force here called AY. So to get what's happening on the pin here, then we need to find out what is AX and AY. And let's do that math somewhere here to make this easier. So basically this is the story. The sum of all the forces on the X direction going positive in that one equals 0 equal, then what we have, AX is positive, then the only force on the that will cancel out with this AX is the tensor force going that direction, and we got that value. That value is coming from here, minus 1200, right, equals 0. Easy. AX is just 1200 Newton. How about the sum of all the forces on the Y direction? Positive in that direction equal AY going up, but then you have this force going down and that force on F1 and F2 somewhere here. Took a while to get this done. Let me copy all this. Right there. So we got AY is up, but we have this force and this force going down, so that will be minus 724 minus 1448. Those are two negative, but the tensor is going up, and that part is this 900 plus 900 equals 0, meaning the AY equal 1448 plus 724 minus 900. Finally, AY is C. Calculator here. 1272 Newton, meaning that the magnitude of A, point A, the pin A, is equal to the square root of 200 square plus 1272 square, and that's about square root of and that's about 1749, or about 1.75 kilonewton. Wow, that took a while. That's why this type of problem on 2 dimension, you definitely want to do this on scalar analysis, not in vector analysis, because again, it's an overkill, but it's a good practice, so you understand the basis and where things need to be applied or not. And so those are the results, basically using vector analysis. If I go back and do this here, let's see where I can do this so you can see what I'm going to be doing. If I want to do this using scalar analysis, it's very straightforward on the fact that I only need this perpendicular distance between this vector here and this distance, which I already calculated. I need this distance, which I already calculated, and break this guy in two parts, like one going up, and call that, like for example, cy, or better than that, ty. And you need also one going this way, that's called tx. So we need these two guys. We already know them because they are right here. On the tx is this 1200, and the magnitude on the ty is 900 going up, and that will affect as well the moment here. So if I want to take that moment right there, I'm going to do it right here. So the moment at A, using a scalar, let's say positive in that direction, equals 0, equal, and here we go. What we have in this direction is called bx, it's called this force 2F2. So we're going to calculate this moment around MA, and this is a story. Let's say that you don't know these values of F. You don't know them because we're going to be doing a scalar analysis. So we don't know those values. So basically what you have is, in this case, is F1, which is happen to be 2F2. I can put 2F2 here, no problem. 2F2 times the distance from here to here, and that distance, let's call that distance dx because it's a shorter one, and dx was calculated somewhere here. That's 1.3, so that time 1.3, and then plus F2 times the longest distance. That's because this is the arm for that one. That's going to be bx, and bx is 2.17. And now what's going to happen with the tensor? I have a tensor that, if we know how to break it apart, is 900 going up, plus this will be 900. Let's see, but that 900 is going on the other direction at the moment. These two are going on the positive, but this is going up, so that means that it's not positive here, that is negative. 900, and then multiply by the arm. That's gonna be the same distance here. That's gonna be 2.17 minus because this tx, then the only distance I care will be about by, this distance here. So that will be the 1200 multiplied by by, and by is 1.25. Now so when we check this out, we see that that's already right here. When you was doing the cross product, that kind of show up. Let's see where it is. Right here, see, that's where it show up. 2.17 times 900 minus, that will be positive, and that's where this number come from. That's right there. So interesting, you see. So what basically is happening is this will go to the other side, and you end up with the same number, which is 3,453. 3,453 equal, then F2 is a factor here, and you end up being 2 times 1.3 plus 2.17, and when you add those two, end up being that F2 is equal to 3,453 divided by the sum of these two guys, which we saw them already on the cross product. 2.17, 1.3 times 2. You see, that's 4.77. So the result is finally that's gonna be 723.8, or about 724 Newton. So check how simple we did the problem on a scalar analysis versus doing cross product. Again, I'm not saying, well, what I'm saying is that There's I don't know, when you do cross product, definitely is fun when you are in 3 dimensions. You can certainly do cross product in 2 dimensions, but the shorter version, in this case the scalar analysis, is straightforward. And you can, I demonstrated here that basically with 2 lines I got the result versus all this to get finally the, just to set up the 3 cross products that were required to finally do the determinant for those 3 matrices to finally get the results as shown here. Well, I don't know, that's more than enough. And as I always said, have a great day, whatever be your final destination. Bye.
Thank you.